For what we know, radiation and matter account for 24% of the total density of the universe. What then accounts for the rest? Scientists believe the source of the missing density is some mysterious form of energy that cannot be detected through its gravitational effect. This energy does not emit any detectable form of radiation, and it does not interact with matter or light. And this is not all. Scientists were shocked to discover this energy is actually working against gravity, and it is a repulsive force driving the galaxies apart, contributing to the acceleration of the expansion of the universe. They call this force dark energy. Dark energy is dominating space, causing the universe to fly apart faster and faster. It has been assumed that the expansion of the universe would slow down eventually, but scientists realized that the universe was speeding up. From the Big Bang, the space in between the galaxies has been expanding and never stopping. The concept of dark energy was introduced in 1998 when scientists researching type 1a supernovae in distant galaxies discovered they were dimmer than expected, meaning they were further away than expected. The only explanation for this phenomenon was that the universe has been speeding up. This evidence suggested that the acceleration started about 5 billion years ago, when the universe was big enough, galaxies were already far enough from each other, so dark matter was dispersed, its gravity weakened and overwhelmed by the repulsive force. So the universe began to expand at an accelerated rate. Ever since, dark energy continues to push, causing the expansion of space to speed up. We owe the concept of dark energy to Einstein. He was convinced that the universe is static, not contracting and not expanding. But his theory of relativity did not equal a static universe. Einstein proposed a repulsive vacuum energy that would hold the energy in balance with the attractive gravity, the cosmological constant that holds the universe in balance. In proposing his cosmological constant, Einstein was trying to suggest that the universe is filled with a form of energy that tends to contribute to the expansion. The force associated with the cosmological constant is a type of anti-gravity, as it makes matter to repel. But in 1929, Edwin Hubble discovered that galaxies are moving away from Milky Way, with farther away ones moving faster. The greater the distance, the greater the speed with which they are moving away from us. When Hubble discovered the expansion of the universe, Einstein came to regard the cosmological constant as a mathematical contrivance, having very little to do with the real universe, and discarded it, calling it the biggest blunder. Einstein invoked the cosmological constant for exactly the opposite reason than it represents now. Today, we use the cosmological constant to define dark energy, the cause of the expansion of the universe, whereas Einstein invoked it for proving his belief that the universe is static. I am as big a fan of dark matter and dark energy as anybody else, says astronomer Richard Ellis of Caltech. But, he adds, I find it very worrying that you have a universe where there are 3 constituents, of which only one, the ordinary matter, is really physically understood. When you teach undergraduates and they say, well, what is dark matter? Well, nobody is really sure. What is dark energy? We are even less sure. So you have to explain to a student that 90 or 95% is in 2 ingredients that nobody really understands, says Ellis. This isn't really progress. What exactly is dark energy? The name we gave to this force actually suggests our unknowingness. It could be an undiscovered particle in the universe performing an anti-gravity interaction or a property of the space-time fabric.
Dark energy is the energy of the vacuum, the energy of nothing.
One discovery of the quantum theory is that vacuum or empty space is not actually empty, and therefore dark energy could be a property of space. Some scientists believe dark energy to be smooth, uniform, since the same amount of acceleration happens in all directions, constant, and its distribution has structure. This uniformity could be the cause of the dark energy's huge impact on the fabric of space. For now, we have to accept that we do not fully understand what dark energy is. But if the acceleration continues, the galaxies will eventually move beyond the cosmic horizon and no longer be visible. Dark energy will break all the gravitationally bound structures, ending the universe in a big rip. It could also disappear with time, or lose its repulsive power, leaving gravity to rule space, leading to the contraction of the universe in a big crunch. Either way, dark energy is a death warrant to all life in the universe. Dark energy brings up the greatest cosmological question of the 21st century, a beginning of a new era dominated by the dark side of the universe. If dark energy is uncovered, the ultimate fate of the universe might be revealed.